Okay. So when solving a trigonometric equation, you'll be using all the identities you've seen so far to basically figure out the answer for x for the equation. Okay. So to start off something simple, like we looked at the first 5 here. These are really easy. Okay, and they're also not actually a matter of solving the equations. It's a matter of just seeing if the given answer works. So like for number 1 here, we've got 2 cosine of x minus 1 equals 0. And we're told to test this out for the points pi over 3, and the other point was 5 pi over 3. Okay, quick question. How would I test this out? What would I do? I just plug and chug, right?
Yep.
Just plug it in and see what I get. Now, if I was doing this without a calculator, how would I figure this out? What would I reference? Unit circle, right? I look at my unit circle and say, okay, pi over 3, that's up here, right? Here's where pi over 3 is. What's the x-coordinate at pi over 3? It's 1/2, right? So that means for A, if I put pi over 3 in this, I have 2 cosine of pi over 3 minus 1 equals 0. That'd be 2 cosine, 2 times 1/2 minus 1 equals 0. Is that true?
Yes.
Yeah. So it works for A. Okay? Now, where's 5 pi over 3 on the circle? It's down here, right? Okay? What's the x-coordinate down there equal to? Negative 1/2, right? So if I put that in there, or negative root 3 over 2, right? No, that's, sorry, I'm getting, oops. 5 pi over 3 is down here. Yes, we're 5 pi over 3.
I think it's...
And it's negative 1/2 is the x-coordinate there. So if I pop the negative 1/2 in the cosine, or sorry, if I popped in 5 pi over 3, the cosine of x is equal to what?
Shouldn't it be on the other side of the y-axis?
Minus
5 pi?
Wait, that's not
hang on.
1 pi.
Pi over 3, 2 pi over 3,
That's not a pi.
4 pi over 3, 5 pi over 3. Right. Thank you. Here's what 5 pi over 3 is. Okay. And so what's the x-coordinate 5 pi over 3? Positive 1/2. So does it work? Yes. Okay. So for these evaluations, this is what you end up doing. Okay. You plug in the values to see what you get. Do you think there's another way I could have solved this without just plugging and chugging? Let's say you weren't given the answers. Okay. So you weren't given these numbers here. How would I have solved them? What can I do?
Oh, add 1 and then...
Yeah, I could shuffle the 1 over, right? So we get this to be 2 cosine of x equals 1. Then what? Divide the 2 out. And so now it's just asking, well, when is the cosine of x equal to 1/2? Okay. You do the arc cosine if you wanted to. Or just look at the unit circle and say, okay, where is the cosine equal to 1/2? Well, pi over 3 it does. And you'd also see it's also equal to 5 pi over 3. So you don't even necessarily need to use the arc cosine. You just look at the unit circle of pi. Okay? So that's kind of another way to do it. So everyone kind of get the idea here? Okay, let's look at number 3. For number 3 here, we've got 3 tangent squared of 2x minus 1 is equal to 0. Okay? So, oh boy, that's a lot going on there. Okay? And so we're going to evaluate this. We're going to take a look at it at pi over 12. Okay? And at 5 pi over 12. Okay? Before we just plug and chug in these numbers, okay, which I'm going to kind of hide up there, how do you think I would handle something like tangent squared of 2x minus 3 tangent squared of 2x minus 1 equals 0? How would I start going about doing it? Yeah?
Add 1 divided by 3 and then square root the whole thing.
Okay, good. So we just start cleaning this thing up, okay? We would basically rewrite this as 3 tangent squared of 2x is equal to 1. Then divide the 3 And then, excuse me, take the square root of both sides, and the tangent of 2x is equal to 1 over root 3, which I can rewrite as root 3 over 3, correct? Okay, so,
Would it be? Why wouldn't it be the square root of 1/3? Or yeah.
well, what's the square root of 1/3? When you do square roots, okay, with fractions, the square root of 1/3 is going to be equal to the square root of 1 over the square root of 3, which is what? 1 over root 3. Okay, that's how fractions work. And remember too, I didn't write this up here, but this should be plus or minus. Why plus or minus? Square root, you're going to have two different answers here. Okay, so plus or minus root 3. Now, if I were solving this by hand, what on earth do you think I would do at this point? Okay, so if I was, or rather not by hand, but with a calculator, I would do what from here? Okay, how do I get the tangent? Okay, how do I get the 2x out of the tangent?
Divide both sides by 2.
No, can't do that. That 2 is locked up in that tangent. Okay?
Minus.
Arc, yeah, I'd use the arctangent, wouldn't I? Because if I did the arctangent to the tangent of 2x, what happens to the arctangent and the tangent? They cancel, right? So, if I did that, do arctan of the tan of 2x to both sides. I would get then that 2x is equal to whatever the arctangent of plus or minus root 3 over 3 is equal to, okay?
How do you also get square root of 3 over 3 is equal to 1 over 3?
Oh, 1/3? Okay, quick reminder, guys, how you rationalize an answer, okay? Whenever, I don't care if you do this or not, okay, and I will put that on the record. I don't care if you do this or not, okay? But technically speaking, when you have you're not supposed to have a radical in the denominator, okay? Some stodgy old mathematician in the 18th century made that rule up, okay? They said, no radical, yeah, something like that, okay? That's a load of stupidity, okay? Really what it comes down to, right? But technically speaking, you're supposed to rationalize it because that's what you're supposed to do. And so when you rationalize it, you basically get the square root out of the denominator. The only way you can do that, okay, is to multiply this thing by basically 1, but in such a way that when you multiply it, the square root goes away. So if you square a square root, it goes away, right? How do I square a square root of 3? I multiply it by square root of 3. So I have to multiply the bottom by the square root of 3, but to not change the value of anything, I also have to multiply the top by the square root of 3. Okay? And so if I did that, 1 times root 3 is root 3, and root 3 times root 3 is 3. Okay? So that's how I ended up that way. Okay? So the real question though is, so at this point I can get out a calculator to solve this. Okay? The other problem though is, if I didn't have a calculator, I'd have to look at the unit circle. Okay? And on the unit circle, okay, okay, we'll just write up 2 locations up here. We can figure out the other one in a second. Okay, there are two locations there. Okay, so which one of those 2 locations, okay, corresponds to the arctangent being equal to root 3 over 3? It's a little bit trickier to tell, isn't it? Why? My 2 locations there are what? They have it be 1/2 and root 3 over 2, right? And we're looking for root 3 over 3. So how on earth would I get that from there? What do I have to do? I have to divide y by x. I have to do what the tangent says. Tangent is y divided by x. So, basically, rationalize it may not have actually helped me. I may want to just stick with 1 over root 3, because that kind of tells me where does the root 3 have to be? On the top or on the bottom?
On
The bottom, if we started off with 1 over root 3, okay? So the root 3 has to be on the bottom, which means x has to be root 3. So what do you think root 3 over 3 has to be equal to? Which location? Is it 0, pi over 6, pi over 4, pi over 3? It's pi over 6, okay? So this gives me that 2x, one answer for this thing is that 2x is equal to pi over 6. This is plus or minus root 3, so is that the only location that's going to happen? Okay, so negative pi over 6 is another location, okay, which from 0 to 2 pi we would write as 11 pi over 6. But is there any other locations? Well, so we know pi over 6, that works. We know 11 pi over 6 would work. You said what? 7 pi over 6, would that work? I'd have root 3 over 2, negative root 3 over 2, negative 1/2. If I did that, would I still get plus or minus root 3 over 3? You bet I would. Which also means what else? What other location? 5 pi over 6. Okay? Because we squared this one, because this was tangent squared, there ends up being 4 possible locations where this thing would actually work out. Normally with trig, there are 2 locations, okay, on your unit circle where it will work out. For this tangent one, there are going to be 4 because we squared it, okay? So 2 squared is 4, if it helps you that way. So pi over 6, 11 pi over 6. Well, let's write them in order actually. So it's pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Are all possible answers there. So I'm going to divide each of those by 2. So what would they all be? Dividing. So that means with a fraction, I'm going to do what to the denominator? Multiply it. Okay? So instead of being pi over 6, it would be pi over 12. So pi over 12. What other one? 5 pi over 12. Also, 14 pi over 12. Sorry, not 14 pi over 12. 7 pi over 12. And lastly, 11 pi over 12. All 4 of those are the answers to this thing. So I didn't jam these in here to test them out. I just went ahead and solved it longhand, and that worked. The actual problem was just plug those in to see if they work. The answer was yes, they would.
Why do we have 4 outcomes instead of 2?
I'm sorry?
Why do we have 4 outcomes instead of 2?
Because again, my arctangent is plus or the answer is it's plus or minus root 3 over 3. Okay? If it was just plus root 3 over 3, only pi over 6 and 7 pi over 6 would be my answers. Okay? Pi over 6 because that's where both x and y are positive. 7 pi over 6 because that's where they're both negative. 2 negatives make a what? Positive. Math is probably one of the few disciplines where 2 rights make a wrong. Okay? Yes? 2 rights don't make it wrong, but was it 3 rights make a left? Oh. 1. 2. Yep. Anyway. But there you have it, okay? So this is how you go about solving these things, okay? So I'm not going to do the rest of I'm not going to do 5 here because 5 is just, again, you're just going to be plugging numbers or trying to solve things out or anything like that. Instead, let's move on and look at the second half, the 13 through 33 problems, okay? These are going to be ones where we're actually solving things like this, okay? So 13, it was easy, 17 was easy, and 21 was easy. So let's skip all those, because those are just literally looking at the unit circle and figuring out what the answers are, okay? Let's cut down to ones which are actual equations. Let's see. 21, 27. Let's look first at 31. That should have been one that was in the problem set, okay? So 31, we're doing every other odd. Let's see.
Wait, that would be 25,
it would be
29.
33, okay. So why don't we then do 29? 29 is a great one to do. Okay, so 29, we've got 3 cosecant squared of x minus 4 is equal to 0. Okay? Now, if I can go through, I can get this cosecant by itself. That's generally what you want to do when solving these things, okay? Is get the trig thing by itself, okay? So let's go ahead and do that, okay? So that would give me cosecant squared of x is equal to 4/3, correct? Okay? Now, do I want this to be 4/3? Well, sorry, getting ahead of myself. Do I want this to be the cosecant squared? No. We know how to do things like the cosecant, or the secant, or tangent, but the second you start squaring them, you know, that makes things crazy. So we take the square root of both sides again, okay? And that's going to give me root 4 over root 3, okay? So, or square root of the whole thing, which comes out this way. Now the reason I would write it this way is, what does the root 4 become? 2, and we still have root 3 at the bottom. Okay, and technically these are plus or minuses, so it's plus or minus there. Okay. And what can I do with, what should I do? Should I leave it as 2 over root 3?
Multiply by root.
I should multiply by root 3, right?
So
Rationalize it to make it 2 root 3 over 3. Okay? Now, this gets a little trickier, okay? Cosecant is 1 over y, correct? Okay. So, which answer here, plus or minus, I should say. Okay. So which one of these then, if I did 1 over y, would give me that as an answer? Would it be this one right here? No, right?
No.
Yeah, pi over 3, correct? The pi over 3s would give me this as an answer. And again, how many answers do you think I'm going to get? Why 4? This is plus or minus, and we basically, if the trig thing is squared, you can expect there to be 4 answers. Okay? Regular trig, 2 answers. Squared, 4. So on and so forth. Okay? So the answer here then should be that that the answer for x here should be I should get pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3 are my answers. Because those are all the locations where y is going to be root 3 over 2, plus or minus root 3 over 2, and then when you flip it, you would get this fraction up here, okay? Now, had I not known that with the unit circle, use that unit circle reference, how would I do how would I get rid of the cosecant? What would I have to do? Do I know what gets rid of cosecants? Well, what should get rid of the cosecant? Okay, not the reciprocal.
1 over cosine.
Nope.
Tangent.
So how do I get rid of a sine? So if I have the sine of x, what do I do to it to get rid of the sine part? I use the what? Arc sine, right? So here, I have cosecant.
1 over arc
Okay. Okay, so 1 over arc sine, that would actually work. What would that be called? The arc cosecant.
Oh, right,
Okay?
right, yeah.
The arc cosecant. Now we haven't actually dealt with the arc cosecant. It does exist. Okay? There is an arc cosecant, arc tangent, an arc cosecant, an arc secant, and an arc cotangent. Those 3 things do exist. Okay? But you could basically model it as 1 over the sine, 1 over the arc sine, 1 over the arc cosine, and 1 over the arc tangent. Okay? Especially because on your calculators, that's exactly what you'd have to do. Okay? You wouldn't be able to do this. Most calculators don't have an arc cosecant button, okay, or an arc cosecant function. Okay? Some might. If you have a really fancy one, you might have it, but most don't. Okay? However, I can still handle this with a 1 over arc sine, because if I made this 1 over sine, okay, 1 over sine can still be that. If I turned the 1 over sine back into sine, that thing would flip, wouldn't it? And then it would just work as a regular sine problem. So Again, we could always approach things like that, okay? Any questions there? It's about as weird as they're going to get with trigonometry, okay, as far as like arc sines, arc cosines, etc. Okay? All right, good. So these examples so far have been good, but there's another example I want to show you. This is actually let me pull one out. Let's see, it's a good one. I'm looking for, let's do, sorry, I'm looking for like the perfect one to demonstrate this. It wasn't in our problem set. Okay. Well, number, well, we want to do number 5. Let's do 41. 41 we can make it work. Yes. 41. Okay. So, this was not in the problem set, but this is a good problem to demonstrate how this next type of thing would work. We've got the secant squared of x, okay, minus the secant of x. It's all equal to 2, okay? Now, it's all, yes, equal to 2, okay? Now, as it's currently written, what can I do to this thing? Can I do anything with the secant squared and the secant? Are there any identities that would help me there? Not really, right? Like, I could, I guess, make one of them to a fraction and then add two fractions together, but that's just going to make things way more complicated, isn't it? Okay? So, but what is this beginning to look suspiciously a lot like? A quadratic, isn't it? Okay? And in fact, if I move that 2 over, that looks exactly like a what? Quadratic, right? Okay? Now, you might say, well, how do I deal with secant squared of x as a quadratic? How would I attempt to deal with this? Okay? If any time you see something like this, thing squared, thing, no thing, okay, you're actually dealing with a quadratic equation. And if you want to, if it's too difficult to see how you would factor this or deal with this as a quadratic, replace the offending thing with a single variable. You can always do that. It's called substitution. Okay? I come here and just say, I don't want to deal with secants. Secant's mess in my head. So we'll go ahead and we'll say the secant of x, we'll make that equal to like y. Okay? I don't want to use x because x is already in there. Okay? That means secant squared would be y squared, and I can replace this all with y squared minus y minus 2 equals 0. That should be way easier to see how that factors, doesn't it? What would that factor to, everybody?
Y plus 1, y minus 2.
So y plus 1 and
Y minus 2.
so y plus 1, y minus 2 equals 0. Okay? So I can write my solutions here. I can solve this thing, right? Y is going to be equal to either -1 or y is going to be equal to 2, correct? But are we dealing with y? Now we're dealing with the secant, correct? So I'm going to go ahead and substitute back in and do secant of x equals -1 and secant of x equals 2. Okay? Now those should be a lot easier to handle. So now we've taken something that was difficult and weird looking, treated it as a quadratic, factored it, and got it down to two things which should be fairly easily solved by either looking at the unit circle or whipping out a calculator. Okay? Where's the secant equal to -1? Okay? Well, where's the cosine equal to -1? At
Pi.
pi. Okay, you're thinking sine. At pi, right? So if the cosine is equal to if the cosine is equal to -1 at pi, and the secant is just the flip of the cosine, where is the secant equal to -1? Also at
Pi.
pi. So this gives us then that x is equal to pi. That's one answer. Where's the other answer? 2. Okay? 2 is a little bit trickier, right? Okay, to figure out where it would be. But think about this. 2, and if the secant of x is equal to 2, that means the cosine of x is equal to 1/2, right? So where's the cosine equal to 1/2? There are 2 locations where that happens. At pi over 3 and down here, right? At 5 pi over 3, correct? So, this gives us more locations. This would say that x should be equal to pi over 3 and 5 pi over 3. Okay. What would I do to confirm that these are, in fact, the correct answers? What can I do?
Go to the unit circle.
I could go to the original problem and plug them in, right?
Oh yeah. What was it just above the y squared minus y minus 2?
Oh, secant squared. Secant squared of x minus secant of x minus 2. Okay? Basically, in order to make my life easier to do the factoring here, I converted I made the secant y with it. Okay? You can always do that. Okay? With quadratics.
The original problem wasn't squared, was it?
Oh no, the original problem was squared.
With like the second sequence of x.
So the original problem was this one right there.
Oh, I thought it was secant squared x minus secant squared x. I was really confused.
Oh, that would have been easy. That would have been 0. No, yeah, it's not squared. So, one thing I can always do to test to see if I'm right is plug these things back into the original equation. I could take all these, plug them up there and see if they give me the correct answer. So plug in pi and see if it gives me that answer. Plug in pi over 3, see if that gives me the correct answer. Plug in 5 pi over 3, see if that gives me the correct answer.
How would you plug in square root now again?
Okay, well, how do I deal with something like secant squared with evaluating an answer? Secant squared of x can be rewritten as the secant of x squared, the same thing. So you just evaluate the secant of x and then square the result. Well, secant of x at pi is -1, so this would be -1 squared minus -1. What's -1 squared? 1, and if I subtract -1 from 1, I get 2. Not add, subtract. Minus makes it positive. So, pi works there. We just saw pi worked. If I did pi over 3, guess what? It's going to work. Be 2 squared minus 2. Well, 2 squared is what? 4. So 4 minus 2 is 2. Same thing with 5 pi over 2. 4 minus 2 is 2. That's one way. What's the other way? Like, if I really need to know. What else could I do? I could always, what'd you say? Graph it, yeah. There's no reason why, what about bookmarks? There's no reason why you can't ever graph these equations, okay? And in fact, that ends up being the, kind of the way you want to solve these things, whoops, if you have no clue how they work, okay? If you graph them, so I would come through here and I would say, the secant of x, close parentheses, squared, minus the secant of x, okay, minus 2. And you just look to see where this thing crosses the x-axis, okay? And from 0 to 2 pi, because that's the only parts we're interested in, okay? 2 pi is just slightly more than 6, okay? That's going to happen right here, at pi over 3, at pi, and at 5 pi over 3. Okay? So all 3 of those locations are crossing points. Exactly as we figured out. So notice though on your graphic calculator when you do this, you're going to get how many answers? In an infinite number, right? Because it crosses the x-axis. It's a wave function. So it's going to repeat itself. So typically speaking, we only want to look at a certain window. So be mindful of whatever the window is that they set for you. Okay? And these problems are always for these problems right now, they're always 0 to 2 pi, but they could be something else. They could make it from 0 to pi, something like that. Okay? Any questions? All right, good. What I'm going to look at, what we're going to cover real briefly right now, okay, is we're going to look at a new set. This will be work for you to deal with for tomorrow. We're going to look at a new set of trigonometric identities that can help us solve trigonometric equations. Okay. The set we're going to look at first, and we're only going to do this set today because we don't have enough time to do the other set. But the other set's easy. It's based on this. Are called the sum and difference formulas. Okay? And what these are for is they allow you to calculate by hand trigonometry with angles that aren't the ones that we're usually used to. Okay? For example, let's say I came up here and I said, give me the sine, I asked you for the sine of, hold on 1 second. Sorry, I'm trying to think of a good one to do here. Let me see. Something that you wouldn't see normally. Yeah, how about this one here, okay? Nope, that wouldn't be a very good one either. Sorry, I'm trying to think of a good angle that would work nicely for here. Okay. Oh, we could always just do it in terms of degrees too. I need to think about that. Give me the, tell me what the sine of 75 degrees is. Okay? Someone go ahead and tell me that. How would you figure that out? What would you do?
Arc sine 70.
Oh no, I'm not trying to solve for 75 degrees.
Oh.
So all you have to do is just sine of 75. What would you do? How would I approach that? You take your calculator, right? Go ahead and type it in. You get your answer, right? Okay. How would you do it without a calculator? Crud, right?
Go to the unit circle.
Go to the unit circle. Where's 75 degrees on the unit circle?
Just between 90 and 60.
Between 90 and 60, so it's up in here somewhere, right?
There's not an exact
There's
point.
no exact point. But I should still be able to figure this out somehow, right? And that's what the sum and difference formula are. Instead of trying to figure out what the sine of 75 is, I'm going to break this apart into two things that I actually know the answer to. I know what the sine of 45 is, right? I also know what the sine of 30 degrees is, correct? Okay, so instead of trying to do this, I'm going to make this the sine of 45 degrees plus 30 degrees, okay? Because those are two angles I do know the answers to. Now, the thing is, it's not so clear-cut as just saying, okay, sine of 45 is this, sine of 30 is this, so sine of 75 must be this, okay? They're still being added together. This is still 75 degrees here. But I've now written in a way that's a bit closer to what I have. And if I had some formula that dealt with this, I could then go through and have chunks that I should be able to handle. And that's what the sum and difference formulas do, okay? This, by the way, can be rewritten now as the sine of 45 times the cosine of 30 plus the cosine of 45 times the sine of 30. That's what that's what the angle formula tells me. Each of those I can figure out an answer to, because each of those are on the unit circle. I'll just get their answers, multiply them together, be done. Okay?
So why is cosine?
It comes from what the sum and difference formula is.
Oh.
All right. Okay? That's the sum of difference formula. Sine. Okay, and there's other ones too. They're all on page 380. So, yeah. You gonna miss Monday? Okay. Look online for your notes. Okay. Yeah. That's fine. Okay.